You've probably experienced it. Ask a large language model a straightforward question, and it answers instantly. Ask it something that requires connecting three separate facts across different domains, and suddenly it's confidently making things up. This isn't a bug in the training data. It's an architectural limitation. Modern LLMs are fundamentally next-token predictors operating on static, unstructured text. They don't inherently track how entities relate to each other over time, across documents, or through complex logical chains. That's why the field is rapidly pivoting towards structured knowledge retrieval. Instead of forcing a language model to hallucinate connections, researchers are anchoring them to knowledge graphs. This is the foundation of what we now call graph retrieval augmented generation, or GraphRAG. But early implementations were rigid. They dump a fixed set of triples into the context window, or follow a predefined search path that couldn't adapt when the query got complex or ambiguous. Enter PersonalAI 2.0. This isn't just another retrieval wrapper. It's a dynamic, multi-stage reasoning framework that treats knowledge navigation like an iterative investigation, rather than a static lookup. Let's break down exactly how it works under the hood. When a query hits the system, it doesn't just pass it straight to a vector database. First, it runs a query decomposition module. Complex, multi-hop questions get split into independent, verifiable sub-questions. Each sub-question is then mapped to the knowledge graph through entity linking and relation extraction. This creates a set of initial seed nodes and edges, grounding the abstract query in concrete graph topology. From there, the system doesn't just grab the nearest neighbors. It deploys a constrained, multi-path traversal strategy. Instead of a simple breadth-first search, it evaluates multiple connected subgraphs simultaneously. It scores each path based on semantic relevance to the original query and relation confidence, actively pruning branches that drift into unrelated domains or introduce low-probability connections. But the real architectural leap is the adaptive planning loop. Traditional retrieval-augmented systems follow a linear pipeline: retrieve, then generate. PersonalAI 2.0 uses the language model itself as a dynamic controller. As it ingests facts from the graph, it continuously evaluates whether the current subgraph satisfies the logical constraints of the original query. If it hits a gap, finds a contradiction, or uncovers an unexpected entity, it doesn't just push forward. It dynamically rewrites the next iteration of its search plan. It generates targeted follow-up queries, adjusts traversal weights, and refines its prompt context in real time. This closes the loop between retrieval and reasoning, turning flat text prediction into structured, iterative verification. The benchmarks back this up. On multi-hop reasoning datasets, that dynamic planning mechanism alone pushed accuracy up by nearly 18% compared to static retrieval baselines. Shifting from flat vector search to structured graph traversal added another 6%. And because it's explicitly filtering and validating against a structured topology, it preserved 89% of the source factual content while keeping parsing and hallucination rates remarkably low. Now let's talk about the cost. This iterative, adaptive loop isn't free. Because the system is continuously evaluating subgraphs, re-ranking paths, and regenerating planning steps, inference latency roughly doubles compared to traditional retrieval methods. But in domains where factual grounding matters more than sub-second response times, clinical decision support, legal research, scientific literature synthesis, that compute overhead is a necessary trade-off. You're trading raw speed for verifiable consistency. What PersonalAI 2.0 demonstrates is a fundamental shift in how we architect reliable AI. The bottleneck isn't model scale anymore. It's navigation. By coupling the generative reasoning of large language models with structured graph topology and iterative planning controllers, we're moving past fluent but fragile text prediction. We're building systems that can actually trace logical dependencies, verify connections, and maintain consistency across long reasoning chains. The future of trustworthy AI isn't about making models bigger. It's about giving them a map, a compass, and the ability to change course when the data tells them to. And that's exactly where the field is heading next.